Welcome to the Deep Dive, where we take the sources you share with us, the research, the news, the complex technical reports, and distill them into the essential knowledge you need to be perfectly informed.
And today, we are staring down a threat that is, well, it's absolutely real. It's statistically certain.
And yet it sounds like the plot of a summer blockbuster. We're talking about asteroid impact avoidance.
Or, as the global scientific community calls it, planetary defense.
It really is the ultimate insurance policy for civilization, isn't it?
It is. And when you read through the source material, the urgency isn't rooted in some kind of panic. It's just cold probability.
So the risk of a catastrophic impact, say tomorrow, is remarkably low.
Oh, very low. But the sources all confirm that the danger is a near certainty eventually. That is, unless we proactively take some robust defensive measures.
That distinction, low risk now, but 100% certainty later, that's what really demands a deep dive. We're not talking about hyperbole here.
No, not at all. This is about global security planning across generations.
So what's the definitive threat assessment that guides all this planning?
I think we can turn to the B612 Foundation for that. They're a nonprofit dedicated entirely to this mission.
And they put it pretty bluntly.
With chilling clarity, yeah. They said, it's 100% certain we'll be hit by a devastating asteroid, but we're not 100% sure when.
And this isn't theoretical. We have major recent examples that frame the whole challenge.
Exactly. Two of them, really.
Okay, so give us the scale. What does a devastating impact actually look like?
Well, the planet killer, the extinction level event, is all defined by size. 66 million years ago, an object roughly 10 kilometers wide slammed into the Yucatan Peninsula.
And that created the Chicxulub crater.
Right. And it triggered the KPG extinction event, which, ended the reign of the non-avian dinosaurs. That is the maximal threat we're defending against.
But the threat profile is much broader than just those planet killers.
Oh, absolutely. You don't need a 10-kilometer object to cause a global catastrophe in the modern world.
Right.
Think about the 1908 Tunguska event over Siberia. That object was relatively small, estimated to be only 50 to 80 meters across.
And it never even hit the ground.
It never hit the ground. It detonated as an airburst explosion about 6 to 10 kilometers up in the atmosphere. But even so, the blast flattened an estimated 30 million trees across 2,000 square kilometers.
Wow. And if an object that size, 50 to 80 meters, were to impact a densely populated coastal area today,
the regional consequences would be catastrophic. You're talking akin to a massive tsunami or a major nuclear detonation.
it would shut down global trade, infrastructure.
Massive population displacement.
Yeah.
The goal of planetary defense is to mitigate all these threats, not just the KPG level ones.
So the whole defense mission, according to the sources, it boils down to two fundamental approaches.
Purely based on physics, yeah. It's either modifying the object or modifying its path.
So we either try to modify the object itself.
Right. That means breaking it up, fragmentation, hoping the resulting pieces are small enough to burn up in the atmosphere or, miss Earth entirely.
Or we go with what is the overwhelmingly preferred method.
Which is deflection. We just modify the trajectory of the object by changing its velocity just enough so that it misses Earth.
So our mission in this deep dive is to trace the evolution of that defense strategy. We're going to unpack the intense global hunt for these objects, the competing deflection technologies,
From kinetic punches to gravity tractors.
and the often surprising political and diplomatic landmines that have to be navigated when humanity tries to save itself.
It gets complicated fast.
Okay, so before we can even think about moving a single space rock, we have to find it.
You have to find it, track it, and predict its course with extreme precision.
Which brings us to the global hunt. And the standards for what we actually consider a target, they've changed dramatically over the last 25 years.
They really have. The initial mandate from the U.S. government, which drives a huge portion of global detection efforts, it focused only on the true extinction-level threats.
This was back in 1998.
That's right. NASA was directed to find and catalog 90% of near-Earth objects, or NEOs, with diameters of 1 kilometer or larger.
And they wanted that done by 2008.
Exactly. That 1 kilometer size was the benchmark for a guaranteed global civilization-threatening catastrophe.
And the program, known broadly as the Space Guard program, was actually pretty successful at meeting that target.
It was. Most of the massive kilometer-plus objects that cross Earth's orbit have now been found and tracked.
And thankfully, none of them are currently on an impact trajectory.
Right. But the focus quickly widened. because people recognize the devastating regional impact of those smaller objects, like the one from Tunguska.
Which led to the 2005 George E. Brown Jr. Act.
And this act set a new, much more ambitious and ongoing goal, one that we are still struggling to meet today.
So the goal shifted.
It did. It shifted to detecting and cataloging 90% of all NEOs equal to or greater than 140 meters in diameter with a target of 2028.
And why 140 meters? What's the significance of that number?
That's the size threshold believed to be large enough to survive atmospheric entry and cause devastating, massive regional damage. Think on the scale of a multi-megaton blast.
Capable of wiping out an entire metropolitan area or causing coastal tsunamis?
Exactly. So we're shifting from finding planet killers to finding, let's call them regional threats.
And how are we doing on that 2028 deadline?
We are far behind, unfortunately. As of early 2024, the sources indicate we've only found and cataloged about 34% of the estimated total population of NEOs in that size range.
44%. So that means over half of these significant regional threats.
Roughly 56%, yeah.
Yeah.
They remain completely undiscovered and untracked.
That is the ultimate vulnerability. We're working on deflection technology for objects we haven't even found yet.
That's the race.
So how is the current search effort being executed under the Space Guard umbrella?
The bulk of the heavy lifting is done by ground-based surveys, particularly in the U.S. Southwest. Historically, the Lincoln Near-Earth Asteroid Research Project, or LINEAR, was a powerhouse.
Right, using those two 1-meter telescopes.
And it was so effective that by 2004, it was responsible for finding 65% of all known asteroids.
But the current champion, the most prolific finder, is the Catalina Sky Survey.
CSS, yeah. Operating out of Arizona, they truly optimize for volume and speed. They use a 1.5-meter telescope on Mount Lemmon and a smaller one nearby.
And their whole method is just constantly scanning.
Constantly scanning huge swaths of the sky, identifying those faint little streaks left by moving objects against the background stars.
Yeah.
Their output is just staggering.
And of course, we also have veteran programs like SPACWatch.
Right, Spacewatch, another Arizona-based program. They pioneered a lot of the scanning techniques we use today. These teams are essentially the front line of Earth's defense.
But ground-based telescopes have limitations. Weather, clouds, the atmosphere.
And they often struggle with objects that are optically dark. And that's where space-based observation becomes absolutely crucial.
And that's the role of the NEOWISE mission.
The Near-Earth Object-Wise extension, yeah. NEOWISE surveys the sky using infrared detection.
Which is vital because a lot of these asteroids are made of dark, carbonaceous material. Very hard to spot in visible light.
Exactly. So if they're dark, how does infrared help us find them?
They absorb heat, right?
They absorb solar radiation, and as they travel through space, they re-radiate that energy as heat in the infrared spectrum. So NEOWISE is essentially sensing the heat signature of these objects.
Which gives you a much more accurate estimate of the asteroid's size.
A much better estimate, yeah. Because the brightness in visible light depends on both size and reflectivity. But the infrared heat output depends almost entirely on its size. So this method is incredibly effective at finding those dark threats the other surveys might miss.
And looking ahead, the source material points to the Vera C. Rubin Observatory as the next huge leap in this.
It promises to be a total game changer. It's starting its survey in late 2025, and it'll be able to survey the entire visible sky every few nights with unprecedented resolution.
So that's the technological boost we need to finally start closing that 56% detection gap for the 140-meter class objects.
That's the hope, yes.
So those are the systems for early warning, giving us years or decades to plan. But we need a last resort, a system designed to catch the small, fast-moving threat that is missed.
Or that approaches from the direction of the sun.
Exactly.
That is the Asteroid Terrestrial Impact Last Alert System, or ATLS. It's a global network now with telescopes in South Africa and Chile, allowing it to scan the entire dark sky every single night.
And the name says it all, Last Alert.
It does. If ATLS finds an object, we are almost certainly too late for deflection, at least with current technology.
But the data is still critical.
Oh, it's the difference between a total surprise and a localized crisis management scenario. If ATLS confirms an impact, the data allows officials to identify the affected region, calculate the impact time, and, launch evacuations. It's the firewall against a surprise Tunguska.
This whole process of detection, it leads to this fascinating problem that scientists have to manage publicly, what the sources call the probability paradox.
Ah, yes. where the calculated impact chance goes up, sometimes dramatically, before it suddenly drops back down to zero.
So why does gathering more data seem to temporarily increase the likelihood of catastrophe?
It's entirely an effect of measurement uncertainty, what we call the error ellipse. When a new object is first spotted, you only have a few data points on its position and velocity.
So its potential path is a big, fuzzy ellipse of error.
A very large fuzzy ellipse, yes. And often, Earth falls somewhere within that initial ellipse, giving us a low but non-zero probability of impact, maybe 1 in a few thousand.
But as you observe it longer, that ellipse starts to shrink.
Exactly. And as it shrinks, the calculation of where the asteroid must be becomes more constrained. If the shrinking ellipse still includes Earth, well, the planet is now covering a larger relative fraction of that error region, because the region itself has gotten smaller.
So it counterintuitively raises the calculated impact probability.
Temporarily, yes. It's just a scientific intermediate step. It's only when you get enough precise data, often from radar, that the error ellipse shrinks enough to clearly show that Earth is outside the trajectory. Then the probability drops to near zero.
But this creates a huge psychological and political headache for scientists.
Immense. Because if an asteroid is truly on an impact course, that probability will just keep climbing as the error ellipse shrinks right around Earth.
This is the classic boy who cried wolf dilemma.
It is. Scientists have to balance raising an alarm, which eats into vital reaction time, against the risk of a false alarm. You panic the public over a near miss, and then next time you sound the alarm,
Nobody listens.
that erosion of public trust is a huge concern, which is why this process requires stringent international coordination formalized through the UN.
So let's talk about the UN's role in managing these warnings.
Okay, so recognizing that an impact is a global crisis, the UN established 2 key bodies in 2013, the International Asteroid Warning Network, or IAWN.
And the Space Missions Planning Advisory Group, SMPAG.
Right. IAWN is the global clearinghouse for warning information. They're tasked with sharing validated, credible information among nations.
And they have a specific trigger for an official warning?
They do. They must issue a warning if the impact probability is calculated to be greater than 1% within the next 20 years for an object larger than about 10 meters.
And SMPAG handles the response.
Right. SMPAG coordinates joint studies on the technologies needed for deflection and provides oversight for actual response missions. This group is essential because planning a deflection mission involves some really intense diplomacy.
And finally, we have to acknowledge the ultimate detection problem, the long-period comets.
They are the absolute worst-case scenario. They originate from the distant Oort cloud, so they enter the inner solar system at speeds much, much faster than most NEOs. Our warning time is tragically short.
Measured in months, not years.
Exactly. Which makes that IAWN and SMPAG coordination extremely difficult under that kind of emergency pressure.
So we know where they are, and we know we're racing the clock to find that other 56%. Let's talk about the hard part. What do we actually build to push this thing?
Deflection strategies. And the source material is very clear. Deflection is overwhelmingly preferred over fragmentation.
Why is that? It seems like breaking it up would be a good idea.
The preference is rooted in the elegance of orbital mechanics. Earth is large, but its path is predictable.
If we can just alter the asteroid's velocity enough to delay its arrival by a little over 7 minutes.
Just 7 minutes?
Just 7 minutes. Earth will have moved 1 full planetary diameter in its orbit, and the asteroid misses completely. That tiny velocity change applied early enough means we're safe.
And breaking it up is so much less desirable because catastrophic residual risk. You shatter a large asteroid, you might create thousands of untrackable fragments. Any fragment larger than about 35 meters in diameter would still survive atmospheric entry and hit Earth with substantial force.
So you trade one big threat for thousands of smaller, still dangerous ones.
Exactly. Deflection is cleaner, more predictable, and safer.
The workhorse of non-nuclear deflection is the kinetic impactor, and this technology is now proven reality thanks to NASA.
Yes, the kinetic impactor is the most mature non-nuclear approach we have. The method is simple. You collide a massive spacecraft with the asteroid at hypervelocity.
And that directly alters the object's momentum, nudging its trajectory.
Right. We had precursors like the Deep Impact mission in 2005 that hit Comet Tempel 1, but that was mostly for science.
The true defense test was DART in 2022, the double asteroid redirection test. This wasn't just analysis.
DART was monumental. It targeted Dimorphos, the small 160-meter moon orbiting the larger asteroid Didymos. This was a perfect test case because they could precisely measure the resulting change.
The goal was to change the orbital period by at least 73 seconds.
And the results they blew that away.
By a lot.
By a lot. DART reduced Dimorphos's orbital period around Didymos by 32 minutes. Far greater deflection than predicted.
And why was it so much more effective?
It's what scientists call the momentum enhancement factor, or beta factor. The collision didn't just transfer the spacecraft's momentum. The impact also ejected a huge amount of material from Dimorphos's surface.
Like a high-speed rocket exhaust.
Exactly. That ejecta pushed the asteroid even further off course. The asteroid helped push itself.
So this validated the kinetic impactor method for threats up to about half a mile wide.
Absolutely. DART established this as the most effective, most technologically ready, and globally agreed upon non-nuclear method available for mid-sized threats, provided we have enough warning time.
Which is typically years.
Typically years, yes. And now other countries are pursuing it. China has a mission plan for 2027.
But what if we don't have years? What if we only have months, or the asteroid is just too big for a kinetic punch?
Then we get to the nuclear option, which, despite all the political baggage, remains the emergency plan.
It's the uncomfortable truth of the matter.
It is. Nuclear explosive devices are currently the only option for a viable defense if warning time is limited to a few months or years. NASA acknowledges they have to keep studying it.
And the way this works is completely counterintuitive. It's not about blowing up the object.
Not at all. The preferred method is the standoff approach. You detonate the device 20 meters or more above the asteroid's surface.
So it's not the physical blast wave doing the work?
No, the blast wave is too slow. It's the highly energetic X-rays and neutrons that instantaneously hit the surface. This high-energy radiation is absorbed by the top layer of material,
causing it to instantly vaporize.
in a process called ablation. It creates this intensely hot, high-speed plasma jet that expands away from the asteroid. And by Newton's third law,
every action has an equal and opposite reaction.
that plasma jet acts like a massive burst of rocket exhaust, imparting a nudging force on the object itself.
So just like the DART ejecta, the asteroid is pushing itself, but the energy source is a nuclear explosion.
Making it far, far more powerful. NASA analysis says nuclear standoff explosions are 10 to 100 times more effective than non-nuclear alternatives.
And this method is better for those rubble pile asteroids.
Crucially, yes. This non-contact approach prevents fracturing those loosely held objects, which a kinetic impactor might just shatter into more deadly pieces.
So 2 years warning, you can deflect a pretty big object this way. But there's an even more intense idea for the shortest possible warning time.
The surface and subsurface approach. This is the Hypervelocity Asteroid Intercept Vehicle, or HAIV, concept.
And the goal here is to maximize energy transfer.
Exactly. The HAV would first use a kinetic impactor to carve out an initial crater. Then, a smaller nuclear device is detonated inside that crater.
So you're channeling the energy, creating a rocket nozzle out of the asteroid itself.
You've got it. The crater channels the plasma and vaporization energy, increasing the effective thrust. The models for this extreme scenario suggest a 300-meter-wide asteroid could be deflected,
With how much warning?
with only 30 days of warning time.
30 days. That's the long period comet scenario.
It's the ultimate insurance for that ultra-short warning time, and the model predicted less than 0.1% of the debris would reach Earth. So while it's politically challenging, if you only have weeks, it's the only thing on the table.
So while the nuclear option covers emergencies, most planetary defense planning is about having years or even decades of warning.
Right. And this allows us to use the slow-push indirect approaches, methods characterized by extreme precision and, well, gentle forces.
Let's start with what has to be the most elegant concept. The asteroid gravity tractor. You're using the weakest force in the universe to save the planet.
And that's the genius of it. The concept is contactless. A massive spacecraft is positioned near the asteroid, and it just hovers there using a low-thrust engine.
And that spacecraft's mass, however small, exerts a constant tiny gravitational pull on the asteroid.
A tiny pull, yeah. So the asteroid is slowly being towed off course like a massive deep space tugboat.
And over months or years, that persistent minuscule tug accumulates into a massive orbital chain.
That's it. And the key advantage here is that the force is uniform and non-contact.
Which makes it perfect for those rubble piles.
A perfect solution. It acts on the entire mass simultaneously, so it won't shatter the object. But the trade-offs are significant. It's the most expensive, has the lowest technical readiness, and requires decades of warning.
So if we need a continuous gentle push, what about just harnessing the sun itself? Focused solar energy?
This method aims to use sunlight as the propellant. You deploy very large, space-based concave mirrors to focus solar energy onto a small spot on the asteroid surface.
And that focused energy vaporizes the material.
Ablates it, yeah, creating a jet of gas and dust. And that jet provides the continuous thrust.
So beyond gravity and focused light, there are other contactless push technologies. Ion beam deflection.
Right. This parallels the gravity tractor's purpose, but uses a different force. Instead of gravity, you use a sophisticated ion thruster pointed directly at the asteroid's surface without touching it.
So it's a direct kinetic push, but at the atomic level.
Exactly. It achieves the same long-term deflection, a persistent, controlled push, but potentially with a much lighter spacecraft.
And then there's the mass driver approach, which is brilliant, using the asteroid's own material as propellant.
It is. It eliminates the need to carry massive amounts of propellant from Earth. You land automated systems, robotic miners, on the asteroid.
They scoop up the surface material
And eject it at extremely high velocities using linear accelerators. Essentially, throwing the asteroid's rocks away quickly to move the asteroid in the opposite direction.
And finally, there are methods that are almost passive, relying on just manipulating the asteroid's relationship with the sun.
These are the reflectivity methods. You can get a deflection just by altering the asteroid's surface. One proposal is to literally paint or dust the surface.
How does changing the color change the trajectory?
Two main ways. First, direct radiation pressure. If you coat the asteroid white with, say, titanium dioxide dust, it acts like a giant solar sail. The photons reflecting off the surface impart a tiny momentum push.
Okay.
Second, and more profoundly, through the Yarkovsky effect. This is a subtle but powerful form of thermal thrust. An asteroid rotates, so one side is heated by the sun and the other side cools. As the heated side rotates away, it re-emits that energy as infrared radiation.
And that delayed heat emission acts like a continuous tiny jet.
Precisely. That recoil force can significantly alter the orbit over long periods. If you paint the asteroid black, you maximize absorption, increasing the power of the Yarkovsky effect. It's incredibly subtle, but with decades of warning, it works.
We've established a robust technological toolkit from nuclear blasts to gravitational tows, but having the technology is only half the battle.
The other half is the political, legal, and diplomatic nightmare that comes with the decision to use it.
The diplomatic minefield. And it starts with the dual-use dilemma.
A concern famously articulated by Carl Sagan. He argued that any technology capable of deflecting an object away from Earth could logically be weaponized to steer a non-threatening object toward a specific point on the planet.
Turning a natural occurrence into a targeted, man-made kinetic weapon.
And his conclusion was stark. He suggested delaying development until an emergency, citing the risk that humanity posed a greater danger to itself than nature did.
But the technical analysis suggests the nuclear option might be too blunt to be a reliable, targeted weapon.
That's a crucial counterpoint. Analysis of the standoff approach shows that while a nuke can change an asteroid's velocity enough to push it out of an Earth-impacting orbit, that change comes with uncertainties, maybe plus or minus 20%.
So you can save the planet, but you can't hit a specific city.
Exactly. You can guarantee a miss, but you can't guarantee a hit.
The most unique diplomatic challenge, though, comes from those slow push methods, like the gravity tractor.
Yes. This is the diplomatic quandary of the shifting impact point. Because the gravity tractor is so slow, the predicted impact point on Earth is constantly moving across the globe as the trajectory changes.
So to achieve a successful deflection, the process of towing it means that for 6 months, the revised impact point might graze over Europe, and for the next year, it threatens China before finally shifting out into space.
That is the core of the problem. You are minimizing the total global risk, but you are effectively shifting the immediate threat from one region to another.
Which means the global community has to agree on the direction of the drag, whose security gets prioritized.
It creates a diplomatic situation where the threat isn't the asteroid, but the uncertainty over which nation will take the temporary risk for the global good. It's an unprecedented test of global cooperation.
This has been an absolutely fascinating deep dive. Let's try to synthesize the current state of planetary defense.
The key takeaway is balance, I think. We have validated kinetic capability with DART. That provides a strong, proven defense for mid-sized threats, provided we have years of warning.
But we're still reliant on theoretical and legally fraught nuclear options for the rapid, massive threats where we only have months.
Right. And the technological shift has been profound, moving from crude attempts to fragment things to subtle, targeted deflection.
And we understand the detection challenges now, especially the psychological stress of that probability paradox.
And all this planning happens while the intense global detection effort continues. Projects like CSS, NEOWISE, and the upcoming Vera C. Rubin Observatory are actively trying to chip away at that massive, undetected population of regional threats.
But that 56% gap remains the core vulnerability.
It does.
And this brings us to the final provocative thought we want to leave with you, the learner. Despite all this incredible ingenuity, DART, HAIV, the gravity tractor, the fact remains that 56% of those large regional threats, 140 meters or larger, remain undiscovered.
And we know statistically that one of these will collide with Earth every 5,000 years, unless we do something. So given that our non-nuclear deflection capabilities require years or decades of warning to work effectively, ask yourself this.
What single technological breakthrough in either detection speed or rapid non-nuclear deflection is the world most critically missing right now to fully secure our future against both the known and the undiscovered threats?
Is the solution faster telescopes?
Yeah.
Or is it a kinetic deflection system that can successfully nudge a 300-meter object in just a few weeks? Something to consider as you reflect on the ultimate project in planetary security.
That's a deep dive for the ages. Thank you for joining us.